So this is part 2 of the Intro to Neural Network series, and in this video, I'm going to be plotting the root mean squared error. So what the root mean squared error does is it takes the difference between the predicted and the actual and squares it. So it's similar to the standard deviation formula. You have to divide by n instead of n minus 1 though. So that was to like account for degrees of freedom, but yeah, you know what? Let's just get right to it. So let's let me go ahead and run this code that I have here. So I'm going to open terminal. Let's just see what this outputs. So I'll do Python 3 intro to nn2.py. So it's going to take a little bit to like gather its thoughts, so to say. I don't know. Neural networks can think apparently. Okay, so I got 3 variables that are being tested, and these are just their error. So the error is being minimized as the neural network trains. So that's good. We know that like the math is mathing. So I'll just go ahead and close that. Let me go ahead and open a new terminal. So let me actually delete this terminal now. So what I want to do is I need to first predict. So let me do this. I don't think I need self.the errors anymore. So I will come over here and take it out. Oh wait, no, didn't mean to do that. My MacBook's fucking up. Okay, so the neural network is going to train, and then I'm gonna have something in here called def predict. This takes the argument of self and x. So I believe this will be it'll probably be like the same dimensions that we have here. So it'll be 4. Let me add some space. So I'll do it like this. For I in self dot axis. Is that what I called it here? Yeah, self dot axis. If I equals self dot axis 0, this will be. So I need the bias as well. So bias is going to be -1. Let me just make sure. Yep, -1. So then this will be self dot. Oh, actually, so this is what happens when you're using PyTorch, which I'll cover in a later video. But there's something called withTorch.noGradient. You don't want to alter the weights of the neural network. So what I'm going to do is I'm going to come here and do w equals self.w, l equals self.l, and sl equals self.sl. Okay, so now it won't affect with the existed training model. So I will come here and do L of I equals x dot transpose dot dot self dot w of I plus bias. And then if it's not the first element, it'll be L of I equals. So let me go back up here and reference this. This will L of I plus 1 transpose. Where'd it go? Self dot, no. L of I plus 1 dot transpose multiplied by self dot w of I plus bias. And then over here it'll be SL of I equals self dot sigmoid of L of I. And then I believe that's it. So those will have the predicted probability. So return SL. So the training is the same. Let me go ahead and delete the plots for now. So this trains the model. So if I want to do predict equals model.predict, let me think of another. I'll do xp equals 1 1 0 0 0 1. So I want to see the prediction between these two. So I will just go ahead and do xp and then print prediction or print predict. So I'll come over here to new terminal, and then I'll do Python 3 intro to and then 2.pi. X has no transpo. Oh, right. My mistake. This is going to be x equals numpy array of x. So clear that. Okay, so I have the variables. Oh, it's because I need to return the last one. So that's gonna be, let's see. I could do it like this. Self dot axis -1. Let's see what happens there. Okay, perfect. So we get the predicted values returned. Um, so now what I want to do is compute the root mean squared error between these. So okay, so now in order to do that, I'm gonna have to completely change this whole thing up. So let me come over here. So I'll do x equals numpy.random.random. So I'll set it to 50 by 5, no 6, and then y is going to be equal to numpy.random.rand. So this is going to be also 50 to 3. So let me actually change this to 7. So then I will do so prop is going to be 0.8, and then I will do I equals the integer of prop times the length of x. So train x is going to equal x to I. Train y is going to equal y to I. And test x is going to equal x of I to the end. And test y is going to be y of I to the end. So I'm going to be calculating the root mean squared error of the predictions. So now in order to do that, I have to collect, let's see. So I can do for tx, ty in zip, train x, train y. So I'm going to initialize my machine learning model. So I'm going to do model equals, I'll call it big AI or little AI? Little AI, and let me just do the arguments. So inputs, outputs. So this will be AI of inputs, which will be 7, outputs, which will be 3, and then model dot build, no, not model dot build parameters. Let me just double check. So over here, it'll just be model of tx, ty, and then it'll be pred equals model dot predict. Is that what I called it here? Yeah, model dot predict of oh wait, no. This comes way after. So this will be for ttx, tty in zip, test x, test y. This will be, oh wait, I need the colon. So this will be test x. So let me go ahead and print predict and break the loop just to make sure the math is mathing. I guess it's not. So wait, is it even rand? These are so confusing. Half of these don't take parentheses. The other half do. It's so fucking annoying to like deal with it. So run it. 710, 76 not aligned. Okay, so, oh wow, that was the error. It's supposed to be TTX. Okay. Okay, so I got the predictions, broke that line. So then it's going to be R residual equals TTY minus predict squared plus equals. So I'll come over here and do residual equals 0. So then it's going to be residual equals numpy dot square root of residual divided by the length of test x. So this is actually, no, not even residual, RMSE. So this is going to be RMSE plus the sum of these squared. So then I'll come down here and do RMSE of, and I'll call this RMSE. So then I will print RMSE, root mean squared error. So clear that. Okay, so this model's RMSE is this. Okay, so let me go ahead and erase that. So now I want to build a plot between the number of epochs and the number of learning rates. So I'm going to come back all the way up here to AI and introduce a new parameter called LR equals 0. I'll do LR equals 1. So then this will be self dot LR equals LR. And the learning rate is just going to be multiplied by the gradient. So this is going to be self.lr times gradient. Yeah. Okay, so now I'm going to come here and anytime I call model, actually, it's going to be better done around here. So I'm going to keep my data dimensions how they are. I'm going to build XB, YB, or rather, no, let me do it like this. Epochs list equals 10, 20, 40, 80, 100. So it's 5. I'll do 150. So 6. And then learning rate is going to equal 1. No. So if there's 10 epochs, oh no, these aren't going to be directly mapped. So I'll do 0 0.1, 0 0.01, 0 0.001, 0 0.0001, and 0 0.00001. So there's 5. I'll just do like 0 0.5 as the learning rate. So now I will do xhyh equals numpy dot mesh grid. 1, 2, 3, 4, 5, 6. Epochs list and learning rate. And then zh is going to be numpy dot zeros of 6 by 6. Okay, so now I'm going to copy this, tab it over twice. So what I'll do here is I'll do for I in range 6, and then for j in range 6. Okay, so it's just going to be z of ij equals RMSE. So epochs is going to equal xh of ij, and then learning rate is going to equal yh of ij. So we can keep it in the square. I'm also going to print out I and j, just so we don't lose track of them. But what I need to do is add the 3D plot function. So it's going to be from matplotlib dot, no, not matplotlib, from mpl toolkits.mplot3d import axes 3D. Do I have the figure? Yeah, I already have the figure. I just have to come here and do projection equals 3D. Okay, so ax.set title RMSE ax.set label. So epochs, or no, not set label, set x label, which is going to be epochs, and ax.set y label, which is going to be learning rate, and ax.set z label, which is going to be the RMSE, and I'm going to set the title ML model performance. Okay, so I got that. So now I'm going to come down here and do ax.plot surface of x xh yh zh cmap equals jet reversed, and then plt.show. So now run it. Okay, so it's a good thing that I only set 6. My computer's slow as shit right now, so it's not gonna perform well. So there's 4, 5. Please run. Okay, so let's check this out. So okay, so hold on, where to start? Okay, so epochs and learning rate. So we could see that the root mean square is the highest when both epochs and learning rate are the highest, which is not good. We want our root mean squared error to be as low as possible. And we can see at the minimum, we have 40 epochs and between 0 and 0.1 learning rate. So that is the perfect, like, it's the perfect time combination. So here, this is what I'm going to do. I'm going to spend some time generate a bigger curve.